Hi, my name is Christian Hall, and today I'll be talking about light. So, what is light? Besides the one sole thing that's keeping us alive on Earth? Well, let's go from the very beginning. The sun. This is the sun, and on it there are probably hundreds of billions of trillions of atoms. Let's take a look at just one of those atoms. So, this is what, think of an atom, you have your protons, your neutrons, and your orbiting electrons. Now, say that atom gets charged by thermal or any other means, and it releases a photon. Now, I want you to remember this word because we're going to talk about it later. Photon. Alright, held inside this photon is what is called an electromagnetic wave. This happens when electric and magnetic fields meet. And so, once they meet, they begin to form a steady pattern. So, the red is going to be the electric field, and the blue is the magnetic. There are three very important things about electromagnetic waves that I want to talk to you about. The first is amplitude. Amplitude is the distance from the middle of the wave to the peak, to the top of the wave. So, right here, that would be amplitude. Right here, that would be amplitude. And right here, that would be amplitude. Next, I want to talk about wavelength. It's the distance between where the amplitude peaks, or the distance between the oscillations in the electric fields. So, in between these two would be the wavelength, or in between these two would be the wavelength. Right? Let's move on to the photon. Now, what is a photon exactly? Well, a photon is a little pocket of energy where the electromagnetic wave is stored. It is massless, yet it is a particle. Now let me show you a little demonstration of what happens. Photon is racing towards an atom and hits the atom. The atom absorbs the photon, and the electrons orbiting the atom go into a higher state of charge. They become supercharged. Then that atom releases another photon, but only at between a certain color range, because atoms act as dampeners. They dampen the light to whatever color they can let through. So, like, green objects can only let out green light. Yeah. But let's talk about the math side of light now. The speed of an electromagnetic wave is represented by the equation V equals F lambda. This symbol right here means wavelength. And this F means frequency. So if you times the frequency by the wavelength, you get the wave speed. Another important thing to remember is that as the frequency goes up, the wavelength is going to shorten. I want to talk about my theory. I think that this theory of light is okay, but I have come up with my own theory of light. So in my theory, here is an atom. begin with the protons and the neutrons and the electrons. Okay. In this, I call it the photospheric theory. An outside force, either thermal or another energy, supercharges the atom, making the electrons move very, very fast and become really charged. This starts to cause disturbances in the electric and magnetic fields. So it continues to make disturbances until the disturbances begin to create a spheric pattern. These spheric patterns then begin to expand. So as the photosphere is expanding, the electric energy, the electric fields, are gathering where the magnetic energy on the magnetic field is the strongest. So this sphere is the magnetic field. And these little groups of orange are the electric fields. Now, the electric fields are what I believe are the photons. There's that magic word again. So, what happens is this light eventually hits an atom. Away from our little demo up there and show you up close. So this is the atom, and this is the field. Now these little groups of the electric field, or the photons, at least one of these is going to hit this atom. And so what's going to happen to the atom? Well, the atom becomes charged, like I show you at the beginning of the photospheric theory, and it's going to release its own. But remember what I said before with the electromagnetic theory, that atoms act as dampeners? It's because they do. So, in my theory, the wavelength is the distance that the photon is vibrating back and forth on the magnetic field. And when this atom begins releasing its own field, the wavelength is going to be slowed down. Wavelength and frequency. The wavelength is going to become shorter, and so it creates different colors. An important thing to remember is that in my theory, all white starts out white. It's white. It's vibrating so fast that it's white. But then it's dampened to a certain color by an atom. Okay. I determined that the force of the electric fields, so E, F, is greater than or equal to the force of the electric fields. Magnetic fields, I mean. Alright. Well, I'm just about finished up. There's just one more thing I wanted to tell you. It is not the job of a scientist to believe everything he hears. It is the job of a scientist to challenge the ideas of what people think is true. And what famous scientist do you think said that? No, it wasn't a famous scientist. It was me. But it is true. Think about all the scientists that have challenged other scientists' theories. Albert Einstein, for instance, challenged Newton's theory of gravity by coming out with the special and general theories of relativity.